Assalamualaikum warahmatullahi wabarakatuh. My name is Amni Izyan Kanan. My ID number is 2019884254. The title of my final year project is Analysis of a Spiral Fin Integrated Heat Recovery Module using Computational Fluid Dynamics (CFD). Before I proceed with the presentation, let me explain a bit about the title. Okay, before this, the title of my project was Development of Test Bench for IHR System with Performance Analysis. But my supervisor decided to change it to make it more specific about what I do. It is basically still the same project, but we just changed the title of it. First, let me explain a bit about the summary of this project. Waste heat recovery is the practice of recycling heat energy that will otherwise be discarded or simply discharged into the atmosphere. By applying the system, air pollution can be reduced. The design of the heat sink is based on spiral fin. The reason why we choose spiral fin because it have an excellent heat transfer rate. Theoretical modeling will be used to obtain the design geometry with a minimum hydrogen preheating temperature of 10 degrees Celsius being the goal. CFD will be used to simulate the performance under different waste heat and cooling air stream conditions. The result that will be obtained from the CFD simulation is the electrical and heat transfer detail characteristic from the integrated heat transfer design for further improvement. For this presentation, I am going to explain about two main components in this system based on the literature review that was done. First is spiral fin tube heat exchanger. Based on the research, optimizing the fin geometry or fin design is one technique to increase the heat transfer rate. The spiral fin has a wide contact area that allows heat to pass efficiently as from the tube surface to the fin. The pressure decreases as the fin pitch decreases and the friction factor will also be decreased. Second, thermoelectric generator (TEG). Based on the Seebeck effect that was initially proposed in 1821, it states that if two different metals are joined at different force and a consequent voltage would exist between them. TEG also was used in converting heat from industrial or road transportation into electricity. It improved the system efficiency and lower the operation cost. This is the example of TEG. It is a small component that has metal in the both sides, which we consider it as hot and cold side. This is the problem statement that were obtained during this project. First, the ability of the heat exchanger to preheat hydrogen gas at 10 degrees Celsius. It is very important to obtain the preheated temperature with minimum 10 degrees because the preheated hydrogen gas will increase the power in fuel cell in order for the fuel cell to generate high temperature of waste heat to the system. Next is the ability of the design spiral fin to increase the heat transfer rate for the system. It is also very important to design a good spiral fin in order to increase the heat transfer rate for preheat the hydrogen. Lastly, the ability to obtain high temperature difference between the hot and cold side of TEG in order to produce electricity. The temperature at the hot side of the TEG need to be as high as possible, while the temperature at the cold side of the TEG need to be as low as possible. This temperature difference will create the electricity in the TEG. The objective of this project is to design a compact integrated heat recovery module for waste heat recovery system of a fuel cell vehicle with spiral fin tube geometry. The components in the heat exchanger and the geometry of the spiral fin were determined by research on the previous study that are related to this project. Next is to analyze the thermal fluids characteristic and electrical power output of the integrated heat recovery system using CFD simulation. CFD will do the simulation of the heat exchanger to determine the flow efficiency of the hydrogen gas and waste heat in the system. The scope and limitation for this project is to design a new heat exchanger using spiral fin with a new fin geometry and dimension. Next, the number of TEG was set to 4 and the number of tube pass was set to 4 pass only. The number of the fin size was taken from the common size and market size, and the calculation to determine the effectiveness of the fin was made based on the dimension. Next, the formula for the calculation was taken from the previous study. Lastly, for this semester, only analysis by using calculation and design using CATIA were done, while the simulation by using CFD will be done next semester on FYP2. So, for the methodology, this is the flowchart for the whole project. At the first phase of this project, I started with identify the problems and objectives that need to be obtained. Then, I proceed with doing the literature review by doing some research on the journal and thesis from the previous study. Upon this stage, I started to determine what components I want to use for the system. Then, I proceed with analytical analysis by using the calculation formula that was obtained from the previous study. Next, I proceed with the design specification and started to design using CATIA. The next step should be CFD simulation by using ANSYS software, but it will done next semester on FYP2. The result of the CFD need to be similar to the analytical analysis in order to consider this project to be done and successful. So, this is the concept of hydrogen preheating for waste heat recovery. The component that will be used is acrylic boards for the hot and cold casing, CPU, copper plate, TEG, tube and insulator, and lastly, spiral fin. The concept for hydrogen preheating for waste heat recovery was developed to have two functions in one system, which is to produce electrical power from TEG and at the same time to preheat the hydrogen gas at 10 degrees Celsius. The spiral fin and hydrogen tube was placed right in front of the copper plate at the hot side. The fuel cell will be the source of waste heat. The hydrogen gas will be inserted in the tube, and the hot air from the fuel cell will preheat the hydrogen at 10 degrees Celsius. The reason why the hydrogen need to be preheated is to increase the power of the fuel cell so that it can increase the temperature of the waste heat that will flow into the system. The flow will be rotated repeatedly. The hot air will not only act to preheat the hydrogen, but at the same time to increase the temperature of the TEG at the hot side. The copper plate was placed in front of TEG at the hot and both sides to increase the heat transfer rate of the both sides. The CPU will be a medium to lower the temperature at the cold side of the TEG. In order to generate the electricity from the TEG, the temperature difference between both sides need to be as high as possible. This is the theoretical analysis where the calculation was made. For this project, NTU method was used to determine the ability of the heat exchanger to transfer the heat. I don't use the LMTD method because this system requires more than one pass tube. Reynolds number also was calculated as it gave a big effect in increasing the temperature of the hydrogen and waste heat temperature. The effectiveness of the heat exchanger also been calculated by using this formula. Next, to determine the overall effectiveness of the spiral fin, the unfin base surface area and the surface area of the fin need to be calculated. Other than that, the efficiency of the fin pitch was calculated by using the Gardner method. This method was discovered during the previous study on the research and journal. So, this is the design of the heat exchanger using CATIA V5. The one with the blue casing is the hot side, while the one with the red casing is the hot side. We also designed the spiral fin using CATIA. Based on the calculation, The outer diameter of the spiral fin is 37.3 millimeters, while the inner diameter is 17.5 millimeter. This dimension will be used for the CFD simulation next semester to determine the exact efficiency, and if it's not achieve a high efficiency, then we will redo the calculation using a new geometry. So, this is the result that was expected during the project, where Reynolds number give a big impact for the system to increase the hydrogen temperature and waste heat temperature. Other than that, the Reynolds number also give effect to the electrical power that will be generated by TEG, which means high Reynolds number will increase the temperature of the hydrogen and also increase the temperature of the waste heat temperature. Reynolds number, the increasing of the Reynolds number also will increase the power generated by TEG. So, that is all from me. Thank you so much for your time.